This diagram compares the blast radius of the weapon that leveled Hiroshima to a standard modern nuclear warhead. In 1945, a single bomb killed roughly 140,000 people. Today, there are over 12,500 nuclear weapons on Earth, each about 80 times more powerful than the one dropped on Japan. It's easy to look at those numbers and assume that if superpowers launch their arsenals at each other, the destruction remains contained to their borders, that as long as you live far away from the impact zones, your life would continue. The explosions are actually the smallest part of the problem. A major nuclear exchange triggers a global climate collapse known as a nuclear winter, a rapid artificial ice age that strips away clean water, breathable air, and sunlight from the entire planet. The terrifying part is that nobody set out to build an atmosphere-destroying weapon. The ability to freeze the Earth was the result of a century-long accidental chain reaction of scientific curiosity. The immediate destruction of a nuclear blast is only the first stage of the event. The atmospheric collapse that follows represents a threat on a global scale, affecting every living thing regardless of its distance from the target. In 1895, Wilhelm Röntgen was playing around with a cathode ray tube in a dark room. He wrapped it in black cardboard, turned it on, and accidentally noticed a chemical plate glowing across the room. He had stumbled onto X-rays. That glowing plate sparked a scientific gold rush. The next year, Henri Becquerel tried to use sunlight to coax X-rays out of uranium. The weather was cloudy, so he shoved his experiment into a dark drawer. When he developed the plates anyway, they were already fogged. The uranium was emitting its own spontaneous radiation. Marie Curie took Becquerel's observation and systematically tested uranium ore. Her investigation led to the isolation of new, highly radioactive elements like polonium and radium. Soon after, Albert Einstein published a mathematical proof that explained where all this invisible energy was coming from. His equation, E equals mc squared, proved that a tiny amount of mass inside these radioactive elements was actually an enormous vault of locked-away energy. The vault was tightly sealed by the atom's nucleus, but in 1932, James Chadwick discovered the neutron. Because it carried no electrical charge, a neutron could slip right past the atom's defenses and split the nucleus wide open. Over 4 decades, these isolated, unintentional discoveries aligned. By the mid-1930s, the scientific community realized they had all the necessary components to manipulate the immense energy density at the center of the atom. By the time the Manhattan Project assembled to build the first bomb, the math revealed a terrifying possibility. Edward Teller calculated that the sheer heat of a nuclear detonation might ignite the nitrogen in Earth's atmosphere, sparking an uncontainable global fire. Chief calculator Hans Bethe ran the numbers again and determined the risk was almost zero. For J. Robert Oppenheimer, almost zero was good enough. He kept the project moving forward, risking the entire planet on a margin of error. The atmosphere didn't catch fire, but when the bomb fell on Hiroshima, it triggered a physical phenomenon the scientists hadn't fully anticipated. It leveled the city, and then it created a monstrous firestorm. Looking at this diagram, you can see how it works. The intense heat of the explosion forces air upward at incredible speeds. To fill the void, cold air is violently sucked inward from the edges. This creates hurricane-force winds that feed the flames, turning the city into a massive, self-sustaining vacuum. That vacuum effect grabs millions of tons of black soot, ash, and burning debris and shoots it straight up, past polar systems, locking it high into the stratosphere. The bomb creates a physical feedback loop. It destroys a city, and then the resulting firestorm acts as a massive injector, pushing millions of tons of debris into the upper atmosphere, where it cannot be washed away by rain. In the 1980s, geologists examining 65-million-year-old rock layers realized that the asteroid that wiped out the dinosaurs didn't kill them with the impact alone. It threw so much dust into the atmosphere that it blocked the sun and starved them out. Dr. Carl Sagan and a team of researchers applied that exact same logic to modern weapons. They ran the math to see what would happen to the atmosphere if the superpowers actually pushed the button. The data was catastrophic. A major nuclear exchange would launch roughly 1 billion tons of black soot high above the rain clouds. Without rain, that soot would spread and wrap the entire globe in a dark, impenetrable blanket. As this chart indicates, up to 90% of sunlight would be blocked. Global temperatures would plummet by 25 degrees Celsius, plunging the planet into a deep freeze. Without sunlight, photosynthesis stops. Within a week, the crops currently standing in the fields would wither and die. The entire global food web would collapse from the bottom up. At the exact same time, the electromagnetic pulses from the blasts would fry the power grid. No electricity to pump water, transport emergency supplies, or heat homes. Humanity would simply freeze in the dark. Calculations of this soot-choked world point to a grim outcome. With the global food web paralyzed, the majority of the human population would face inescapable starvation. And it doesn't even take a war between global superpowers to cause this. Climatologists calculate that a localized nuclear exchange between two neighboring nations is mathematically enough to trigger a worldwide winter. Surviving this requires an extreme playbook. Nations would have to immediately construct subterranean vertical farms to grow food underground, and rely on heavy Faraday cages to protect what little electrical infrastructure remains from EMPs. Our diet would have to radically shift to things like spirulina. It's a highly dense, protein-rich algae that can multiply rapidly in near darkness, taking up very little physical space. But while governments and militaries have spent decades building deep, self-sustaining bunkers to preserve their own leadership, the vast majority of civilians would be left to navigate a frozen, barren wasteland. You might survive the initial flash, you might even survive the firestorm, but you cannot beat a completely broken atmosphere. The only mathematically viable strategy to survive a nuclear winter is to ensure the weapons are never fired in the first place.